Right now, as you're watching this video, you're falling through empty space at incredible speed. Not metaphorically, not poetically, but literally falling through a region of the universe so vast and so empty that it challenges everything we thought we knew about our cosmic neighbourhood. Scientists discovered this in 2013, and somehow most of the world still doesn't know about it. We live inside what researchers call the KBC void, a cosmic desert that stretches nearly 2 billion light-years across. Think about that for a moment. 2 billion light-years. That's a distance so enormous that light itself, travelling at 186,000 miles per second, takes 2 billion years just to cross from one side to the other. And we're sitting somewhere near the middle of this incomprehensible emptiness. Tonight, we're going to explore one of the most unsettling discoveries in modern astronomy, a revelation that's forcing scientists to question whether our measurements of the universe itself might be fundamentally wrong. Before we dive into this cosmic mystery that's been hiding in plain sight, I'd love to know where you're watching from and whether you've ever wondered if our place in the universe might be more unusual than we've been told. And if you find yourself drawn to these kinds of mind-bending cosmic revelations, hitting that like button and subscribing really helps us continue exploring the universe's most fascinating secrets together. Get ready. The journey begins now. Picture 3 astronomers sitting in front of their computers in 2013, counting galaxies like cosmic accountants. Ryan Keenan, Amy Barger, and Lennox Cowie were doing something that sounds almost mundane, mapping the positions of 35,000 galaxies across billions of light-years of space. But what they found was anything but ordinary. The numbers weren't adding up. Everywhere they looked in our cosmic neighbourhood, there were fewer galaxies than there should be. Not just a few missing here and there, but 20% fewer galaxies than cosmic models predicted. The pattern stretched outward in every direction for 1 billion light-years, forming a sphere of cosmic emptiness, with us sitting uncomfortably close to the centre. This wasn't some small gap between galaxy clusters that astronomers had simply overlooked. This was a void on a scale that shouldn't exist according to our standard understanding of how the universe is structured. The researchers checked their data obsessively, used multiple galaxy surveys, examined the sky from different angles, and ran their calculations again and again. The result remained consistent and deeply troubling. Our galaxy, along with everything we can see around us, for hundreds of millions of light-years in every direction, sits inside what amounts to a cosmic bubble of near-nothingness. The discovery earned a deceptively casual name, using the initials of its 3 discoverers, but there's nothing casual about what the KBC void represents for our understanding of the cosmos. In the standard model of cosmology, the universe should be roughly uniform when you zoom out far enough. Sure, galaxies cluster together in some places and leave empty spaces between them, but those variations should average out over large scales. The universe should look basically the same, whether you're observing from Earth, from a galaxy in the Andromeda constellation, or from some distant cluster billions of light-years away. But a region this enormous, with such a significant deficit of matter, pushes far beyond what random chance can reasonably explain. When cosmologists run computer simulations of how the universe evolved from the Big Bang, they rarely produce voids this large and this empty. When they do manage to create something similar, it requires exceptionally rare initial conditions that occur less than once in 1,000 simulated universes. Some scientists have calculated that finding ourselves inside such a void represents what statisticians call a 10 sigma deviation from average cosmic density. To put that in perspective, a 5 sigma result in physics means there's less than 1 chance in a million that you're seeing a random fluke. A 10 sigma deviation is so unlikely that you might not find one in the entire observable universe, yet here we are, living inside one. The implications began cascading through the astronomical community immediately. If we reside in such an unusual location, does that bias every measurement we make about the universe? When we point our telescopes at distant exploding stars to measure how fast space is expanding, are we seeing the true cosmic expansion rate? Or are we getting a distorted local version that doesn't represent the universe as a whole? This possibility offered a potential solution to one of the biggest crises in modern cosmology. For years, scientists have been measuring two different expansion rates for the universe, and they disagree by 9%. Both measurements are incredibly precise. Both should give the same answer if our understanding of cosmology is correct. They don't. One method looks at the cosmic microwave background, the faint afterglow of the Big Bang, and calculates what the expansion rate should be today based on conditions in the early universe. This gives an answer of about 67 kilometers per second per megaparsec. The second method looks at nearby objects with known brightness, like certain types of exploding stars, and measures the expansion rate directly by comparing how bright they appear versus how bright they should be. This local method consistently produces a higher number, about 73 kilometers per second per megaparsec. The difference might sound small, but it represents a fundamental crisis in cosmology. Both measurements have been refined and cross-checked extensively. The disagreement has reached what scientists call 5 sigma statistical significance, meaning there's less than 1 chance in a million that it's just a coincidence. The KBC void hypothesis offered an elegant explanation for this puzzle. If Earth sits inside a massive region where matter is much thinner than average, then gravity from the denser matter surrounding the void would pull outward on galaxies within it. This would add extra velocity to their motion away from us, making the local expansion appear faster than the cosmic average. Suddenly, the conflicting measurements made perfect sense. We weren't measuring the universe incorrectly. We were measuring it from inside a hole in space, and that hole was systematically biasing our observations in ways that made the local expansion rate appear artificially high. But this realization opened up an even more unsettling possibility. If our location is this unusual, can we trust anything we think we know about the cosmos? What if decades of astronomical observations and cosmological theories have been built on measurements that don't represent the universe as a whole, but only our weird local environment? To understand just how strange our cosmic neighborhood really is, we need to explore what it actually means to live inside a void. The term itself is somewhat misleading because cosmic voids aren't truly empty. When astronomers call a region a void, they mean it contains far less matter than average. But matter still exists there, scattered like rare islands in an ocean of near nothingness. In a typical region of space, you might find 10 galaxies in a given volume. In our void, that same volume might contain only 1 or 2 galaxies. The matter doesn't vanish completely, but it becomes incredibly sparse. Between these lonely galaxies stretches space that contains mainly dark matter, dark energy, and occasional wisps of hydrogen gas drifting through the cosmic vacuum. The density is so low that gravity, already the weakest fundamental force in nature, becomes even less relevant to the overall dynamics of the region. Without enough mass to pull things together effectively, structure formation essentially grinds to a halt. No new galaxy clusters can form. No rich collections of thousands of galaxies can emerge. The void stays a void, locked in a state of cosmic underdevelopment. This emptiness has consequences that ripple through physics itself. In dense regions full of galaxies, gravity fights against dark energy, the mysterious force that accelerates cosmic expansion. But inside voids, gravity loses that battle decisively. Dark energy wins, causing voids to expand faster than the rest of the universe, growing like bubbles that push their boundaries outward, while the networks of galaxies around them act as constraining walls. This creates a self-reinforcing cycle that makes voids even more extreme over time. The more a void expands, the emptier it becomes, which allows even faster expansion. Scientists have confirmed this through careful observation, measuring how galaxies near void edges move compared to galaxies in denser regions. The void galaxies are rushing away from the center faster than cosmic expansion alone would explain. Something is pushing them outward, and that something is the gravitational pull from all the matter outside the void. Think of our situation like being in a valley surrounded by mountains, except instead of literal terrain, we're talking about the curvature of space and time itself. Gravity pulls downhill from the mountains toward the valley, but since we're dealing with the fabric of space rather than physical landscape, that pull makes galaxies fall outward rather than inward. The effect is measurable and significant. Our own galaxy is moving away from the center of our local void at roughly 600,000 miles per hour, driven by this gravitational imbalance. We're not just sitting passively in empty space, we're actively falling through it, carried along by forces operating on scales so vast they challenge human comprehension. Inside a void, light travels differently than it does through normal space. Because there's less gravitational influence, light passing through voids experiences less of what physicists call gravitational redshift. This shows up in subtle ways when astronomers study the cosmic microwave background radiation. Light that has passed through voids appears slightly cooler than light that has traveled through denser regions, creating cold spots in temperature maps of the early universe. These cold spots line up perfectly with where we observe large voids today, providing independent confirmation that these enormous empty regions really do affect the fundamental properties of space and radiation passing through them. It's not just that voids look empty when we count galaxies, they actually behave differently at the level of basic physics. Understanding what makes voids empty helps explain why they matter so much to our understanding of cosmology. They're not just boring blank spaces between the interesting parts of the universe where all the galaxies cluster together. They're natural laboratories where dark energy dominates completely and where gravity takes a back seat to the mysterious force that's accelerating cosmic expansion. By studying how matter behaves differently in voids versus dense regions, scientists can test fundamental theories about how the universe works on the largest scales. The KBC void around us might be unsettling because it makes us question whether our cosmic location is typical, but it also offers an unprecedented opportunity to study the universe's most extreme low-density environments from the inside. The structure that contains these voids turns out to be far stranger than anyone imagined when astronomers first started mapping the universe in 3 dimensions. The cosmos isn't organized like a smooth soup of evenly distributed galaxies. Instead, it resembles Swiss cheese, where dense matter forms walls and filaments surrounding enormous hollow pockets of near emptiness. This foam-like architecture is called the cosmic web, and it represents the largest structure in nature. Galaxy clusters concentrate at the intersections where multiple filaments meet, creating nodes of intense matter density that shine brilliantly with millions of galaxies packed relatively close together. Stretching between these nodes run filaments, long chains of galaxy groups that can extend for hundreds of millions of light years, forming walls where galaxies gather in higher than average concentrations. Between the filaments and walls lie the voids, taking up roughly 90% of the universe's volume while containing hardly any mass. This structure wasn't always obvious to astronomers. For decades, scientists photographed the sky and counted galaxies, but the true 3-dimensional arrangement remained hidden because distance measurements were poor. Galaxies that appeared next to each other in the sky might actually be separated by billions of light years, with one much farther away than the other. Only when scientists began measuring galaxy redshifts systematically in the 1970s and 80s did the cosmic web reveal itself. Redshift measurements allowed astronomers to calculate how far away each galaxy was, by measuring how much the expansion of space had stretched its light toward redder wavelengths. Suddenly, the distribution of matter snapped into focus, revealing a universe with structure on scales nobody had expected. The first major void discovery came in 1978 when two independent research teams identified large under-dense regions that seemed to violate everything astronomers thought they knew about cosmic structure. More surveys followed, each mapping deeper into space and revealing an increasingly intricate web of matter and emptiness. The Sloan Digital Sky Survey, which began operations in 2000, created spectacular three-dimensional maps spanning billions of light-years that showed the cosmic web in stunning detail. These maps revealed filaments twisting and branching like blood vessels through space. Voids appeared as dark bubbles, sometimes 500 million light-years across, sitting between the bright networks of galaxies like enormous caverns in a cosmic cave system. The largest structures discovered include formations nearly 1.5 billion light-years long, while on the opposite end of the spectrum, supervoids stretch even wider than our own KBC void, containing even fewer galaxies per unit volume. Together, these features paint a picture of a universe organized on scales far larger than anyone had predicted. Galaxies aren't the fundamental building blocks of cosmic structure. The web itself is the primary architecture, with galaxies simply marking where matter happens to concentrate along its vast framework. We're not living in a universe filled with galaxies that occasionally have empty spaces between them. We're living in a universe of emptiness that's occasionally interrupted by thin threads of matter. But why does the universe organize itself this way? The answer reaches back to the very beginning of time itself. Immediately after the Big Bang, matter wasn't perfectly uniform. Quantum fluctuations during the universe's first fraction of a second created tiny variations in density, some regions slightly denser than average and others slightly less dense. These differences were minuscule, maybe 1 part in 100,000, but gravity amplifies even the smallest advantages. Over hundreds of millions of years, this process snowballed into the cosmic web we observe today. Denser regions pulled in more matter from their surroundings, making them denser still and eventually forming the first stars, then galaxies, then clusters of galaxies. Meanwhile, the under-dense regions lost matter to their denser neighbours, becoming increasingly empty as material drained away toward the collapsing, over-dense regions. The cosmic web is essentially gravity doing its work over cosmic time, turning barely noticeable initial ripples into the grandest architecture in existence. Today, voids occupy roughly 90% of the volume of space, while filaments and clusters make up the remaining 10% but contain most of the mass. This fundamental imbalance defines the character of our universe. The Milky Way's position within this vast structure is both significant and troubling for our understanding of cosmology. We're not sitting at the center of the KBC void, but we're close enough to matter profoundly for every observation we make. Current measurements place our galaxy somewhere between 2 and 400 million light-years from the void's actual center. That might sound like an enormous distance, and it is by any human standard. But the void extends outward for 1 billion light-years in every direction from its center. This means we sit well within the under-dense region, surrounded by the void's low-density environment in all directions we can observe. Our position isn't random, and it has measurable consequences for every conclusion we draw about the nature of the universe. If we were located outside the void entirely, in one of the dense filaments that surround it, our measurements of cosmic expansion would look completely different. We would calculate a slower expansion rate, and the Hubble tension that's currently tearing apart cosmology simply wouldn't exist. Our understanding of dark energy, the mysterious force accelerating cosmic expansion, would be fundamentally different. Even our estimates of the universe's age and composition would change dramatically. Our larger cosmic neighborhood adds yet another layer to this story. The Milky Way belongs to what astronomers call the local group, a collection of about 80 galaxies, including our giant neighbor Andromeda. The local group itself sits within an even larger structure, called the Laniakea supercluster, a massive formation containing roughly 100,000 galaxies spread across 520 million light-years. Laniakea is enormous by any normal standard, containing more matter than most people can even conceptualize. Yet even this supercluster, with its 100,000 galaxies, resides entirely within the KBC void. Think about that for a moment. A structure containing 100,000 galaxies still counts as part of an under-dense region of space. The void is so vast that it can swallow entire superclusters and still have room to spare. Laniakea forms part of the sparse population of matter scattered through the void, one of the rare concentrations of galaxies in an otherwise barren expanse. Our supercluster is like finding a small city in the middle of an enormous desert. The city might seem substantial when you're walking through its streets, but from a satellite view, it's just a tiny cluster of lights, surrounded by endless emptiness. The local group is also influenced by another nearby void called the local void, which is distinct from but connected to the larger KBC void. This smaller void extends about 200 million light-years and sits adjacent to our position, creating additional complexity in the gravitational environment around us. Our galaxy is rushing away from the local void at 600,000 miles per hour, pushed by the gravitational pull from denser regions beyond both voids. This motion is separate from the overall expansion of the universe. It's what astronomers call a peculiar velocity, meaning it results from local gravitational effects rather than the stretching of space itself. These peculiar velocities complicate efforts to measure the true expansion rate because they add extra motion on top of the expansion signal that scientists are trying to detect. Inside a supervoid like ours, these local effects are amplified and much harder to separate cleanly from the cosmic expansion we're trying to measure. The void's influence reaches even farther than our immediate neighborhood. When scientists measure the motion of galaxies out to distances of 250 million light-years, they find bulk flows that exceed what standard cosmology predicts. Entire regions of space are moving faster than they should be, flowing in coherent patterns driven by the void's gravitational imbalance. The KBC void creates a large-scale velocity field that affects everything within it. Galaxies aren't just sitting passively in an empty region, slowly expanding with the universe. They're actively responding to the gravitational landscape, accelerating outward from the underdensity toward denser structures beyond the void's edge. This makes our local patch of the universe far more dynamic and unusual than the calm, uniform cosmos that standard cosmological models assume when making their calculations. Our position inside the void also affects what we can see and how we interpret those observations. Light from distant galaxies travels through the void on its way to our telescopes, experiencing less gravitational interaction than light traveling through denser regions of space. The reduced gravity creates subtle effects on the light's wavelength and energy that can bias our measurements in ways we're only beginning to understand. Additionally, the void itself influences the distribution of matter we observe. When we look outward from inside the void, we see the shell of denser material surrounding us in all directions. That shell appears as a concentration of galaxy clusters and filaments at a specific distance range, beyond which the universe returns to more typical density. This creates what astronomers call an observational selection effect. We're not sampling a random location in the universe when we make our measurements. We're sampling from inside one of its most extreme features, and that fundamentally changes what we see. Living in the void means living with systematic uncertainty about how representative our observations really are of the universe as a whole. Every measurement you've ever heard about the universe's expansion rate, its age, its composition, and its ultimate fate might be influenced by our unusual location in ways that scientists are only now beginning to appreciate. We're not just passive observers of cosmic evolution, we're participants in it, carried along by forces operating on scales so vast they dwarf our ability to step outside them and see the universe objectively. The question that keeps cosmologists awake at night is whether we can ever truly know what the universe looks like from a typical location, or whether we're forever trapped inside our cosmic bubble, measuring a reality that might be fundamentally different from the experiences of hypothetical observers in denser regions of space. The answer to that question will determine whether our current understanding of cosmology represents universal truth or merely the view from inside a hole in space. In space, the problem becomes even more disturbing when you realize what this means for every measurement we've ever made about cosmic expansion. Scientists have spent decades using nearby exploding stars called supernovae to measure how fast the universe is expanding. These cosmic lighthouses have known brightness, so by comparing how bright they appear to how bright they should be, astronomers can calculate their distance with remarkable precision. But here's the catch that's been hiding in plain sight. When we measure the expansion rate using these nearby supernovae, we're measuring within the void. The void's low density means there's less gravity pulling back against the expansion of space. More importantly, matter from the denser regions outside our void gravitationally attracts galaxies within it, adding extra outward velocity to their motion. This makes galaxies appear to recede from us faster than they would in a typical region of the universe. We're not measuring the universe's true expansion rate at all. We're measuring the expansion rate plus the void's peculiar velocity field, and that additional motion is inflating our local measurements by exactly the amount needed to create the crisis in cosmology. The effect is substantial enough that when scientists model how a void of our size and depth would affect local measurements, they find it could boost the apparent expansion rate by precisely the 9% discrepancy that's been tearing apart our understanding of cosmic evolution. The mathematics work out almost too perfectly, which is both reassuring and deeply unsettling. If the void explains our local measurements, then those measurements don't tell us about the universe as a whole. They tell us about our weird local environment. The cosmic microwave background method, which looks at ancient light from when the universe was just 380,000 years old, remains unaffected by the void because it probes conditions long before voids had time to form and influence cosmic structure. That measurement might represent the accurate expansion rate for the universe's global properties, while our local measurements have been systematically biased by our location for as long as we've been making them. This means that most headlines you've seen about the accelerating universe and the mysterious force called dark energy might be describing a local phenomenon rather than a universal truth. We've spent decades building cosmological models based partly on local expansion measurements, and those measurements might be telling us more about where we happen to live than about how the cosmos actually works. The implications cascade through every aspect of our cosmic understanding, like dominoes falling in slow motion. Some scientists resist this conclusion because it violates what's called the cosmological principle, one of the foundational assumptions of modern physics. This principle states that Earth doesn't occupy a special location in the universe. It assumes that the cosmos should look roughly the same from any vantage point once you average over large enough scales. Finding ourselves inside a supervoid that significantly affects our measurements seems to contradict this fundamental idea. It suggests we're in an unusual location, which makes physicists deeply uncomfortable. Science has spent centuries progressively removing humanity from special cosmic positions. Earth isn't the center of the solar system. The solar system isn't the center of our galaxy. Our galaxy isn't the center of anything significant. And now we're supposed to believe we just happen to live inside one of the largest voids ever observed? The statistical improbability bothers many researchers who've built their careers on the assumption that our location is fundamentally typical of cosmic real estate. Yet the evidence keeps mounting from multiple independent sources. The void exists and can be measured through different techniques. Our expansion rate measurements are genuinely discrepant with early universe observations. The void's predicted effects match what we actually observe in galaxy motions and cosmic structure. Whether we like the philosophical implications or not, the universe might actually be providing us with systematically biased information about its own expansion rate. Or more precisely, our location is causing us to misinterpret what we measure, like trying to determine the average temperature of Earth while standing inside a heated building. The crisis this creates in cosmology runs much deeper than most people realize. The expansion rate disagreement isn't just an inconvenient discrepancy between two measurement techniques. It represents a fundamental challenge to our understanding of how the universe evolved from the Big Bang to the present day. Cosmology rests on a framework called lambda cold dark matter, which has been spectacularly successful at explaining observations from multiple independent sources. This model accounts for the cosmic microwave background temperature fluctuations, the abundance of light elements created in the early universe, the formation and evolution of galaxies, and the large-scale structure of cosmic matter distribution. For decades, it's been the consensus model because it works remarkably well across so many different contexts and observations. But the expansion rate tension suggests something crucial is missing or wrong in this framework. When a model's predictions disagree with observations at the 5 sigma level of statistical significance, scientists must take that seriously. The tension matters because the expansion rate determines everything else about cosmic history. If the universe expands faster than we thought, it reaches its current size in less time, making the universe younger than current calculations suggest. Present estimates based on the cosmic microwave background put the universe's age at 13.8 billion years. But if the higher local measurement represents the correct global expansion rate, the universe might be only 12.7 billion years old. That creates immediate and serious problems because we observe stars that appear to be 13 billion years old based on stellar evolution models. These stars would be older than the universe itself, which is obviously impossible. Either our age measurements for stars are systematically wrong, our understanding of how stars evolve and burn fuel is incorrect, or the higher expansion rate doesn't apply to the universe's early history. None of these options provide comfortable solutions, and each would require overturning decades of well-tested astrophysics. The tension also affects our understanding of dark energy, the mysterious component that makes up about 68% of the universe's total energy budget. Dark energy is responsible for accelerating cosmic expansion, but its properties depend sensitively on the expansion rate itself. If the expansion rate is higher than standard models predict, dark energy's behavior might be fundamentally different from current assumptions. Some researchers have proposed that dark energy evolves over cosmic time rather than remaining constant, which would revolutionize our understanding of this dominant cosmic component. Others suggest we need to add completely new physics to the early universe, perhaps an additional burst of accelerated expansion shortly after the Big Bang. Every proposed solution introduces new complications and requires evidence beyond just fixing the expansion rate disagreement. The void hypothesis offers what many consider the most elegant solution to this crisis because it requires minimal modifications to fundamental physics. It simply states that we're measuring from an unusual location, and our local observations reflect that environmental bias rather than universal properties. This explanation bothers people philosophically because it violates our deeply held belief that Earth occupies a typical cosmic location. But it requires fewer new assumptions than inventing new particles, changing the laws of gravity, or completely reworking our understanding of cosmic evolution. Recent work has strengthened the void hypothesis by showing it naturally predicts other observations that would otherwise seem mysterious. For example, the outflow velocity from our void should affect not just expansion measurements, but also the motion of galaxy clusters in our cosmic neighborhood. When scientists measure these bulk flows of matter, they find exactly the patterns that void models predict. The hypothesis isn't just explaining one anomalous observation, it's making testable predictions about multiple aspects of our local cosmic environment, and those predictions are being confirmed by independent measurements. Nevertheless, the debate continues because not all cosmologists accept the void explanation as sufficient. Some argue that even a void as large as ours cannot produce big enough effects to fully explain the expansion rate tension. Others point out that supervoids this extreme should be incredibly rare, and finding ourselves in one just when we develop the precision to measure cosmic expansion seems suspiciously convenient. Maybe we're interpreting the observational data incorrectly somehow, or maybe there are subtle systematic errors in our measurement techniques that haven't been properly accounted for. The controversy remains unresolved, which is why the expansion rate disagreement continues to be called a crisis rather than a solved problem. It's not just a number that's slightly off in our calculations. It's a signal that our understanding of the cosmos might be fundamentally incomplete in ways we haven't yet recognized. The void around us is teaching us that even our most basic measurements of cosmic properties might be influenced by local environmental effects operating on scales so vast we can barely comprehend them. Understanding how gravity creates this measurement bias requires looking at how forces work differently in nearly empty space. Gravity inside a void does something that seems counterintuitive at first. Instead of pulling everything inward toward a common center, it effectively pushes outward in all directions. This isn't because gravity itself reverses or changes its fundamental nature. The force of gravity always attracts mass toward mass, just as Newton and Einstein described, but the geometry of mass distribution matters enormously for determining which direction that attractive force points. Imagine standing in a shallow valley surrounded by mountains on all sides. Gravity pulls you toward those mountains, which means pulling you away from the valley's center and up toward the higher elevations where most of the mass is concentrated. Inside a cosmic void, galaxies experience exactly the same effect. All the significant matter lies outside the void in the surrounding filaments and galaxy clusters. That exterior matter gravitationally attracts everything inside the void, pulling galaxies outward from the underdense region toward the denser structures beyond the void's boundaries. The result is what astronomers call an outflow, a systematic pattern of galaxies accelerating away from void centers toward regions of higher matter density. This outflow is both measurable and significant when you know how to look for it. Astronomers can track galaxy velocities using redshift measurements combined with independent distance estimates. When they map these velocities around known voids throughout the universe, the pattern becomes unmistakably clear. Galaxies near void centers move faster outward than cosmic expansion alone can explain. The effect is strongest near void centers and gradually weakens toward the edges, where matter density begins to increase again. For our specific void, this outflow adds hundreds of kilometers per second to galaxy velocities throughout the underdense region, including the motion of our own galaxy. The Milky Way participates directly in this pattern, moving at 600,000 miles per hour away from the nearby local void, driven by the gravitational imbalance between the empty region behind us and the denser structures ahead. This motion combines with other local gravitational effects to create our galaxy's total peculiar velocity through space. The outflow has direct implications for cosmic expansion measurements that most people never consider. When we observe distant galaxies and measure their redshift, we're seeing a combination of two distinct effects working together. First is the expansion of space itself, which stretches the wavelength of light as it travels through an expanding universe. Second is the peculiar motion of galaxies due to gravitational attractions and repulsions from their local environments. Normally, scientists can separate these components because peculiar velocities should average out when you look at large enough volumes of space. For every galaxy moving towards you due to local gravitational effects, statistical reasoning suggests another galaxy should be moving away, and the average peculiar velocity should approach zero. But inside a void, The peculiar velocities don't average out to zero. They all point systematically in the same direction, outward, from the underdense region. This creates a coherent bias that inflates the apparent expansion rate when measured from within the void, exactly like adding a constant velocity to every measurement. The problem compounds at different distance scales within our cosmic neighborhood. Close to the void center, the outflow reaches its maximum speed. Farther from the center, but still within the void, the outflow velocity gradually decreases. Beyond the void's edge, peculiar velocities might even reverse as matter begins falling back toward the denser filaments. This creates a complex velocity profile that varies systematically with distance from our location. When astronomers measure the expansion rate using supernovae at different distances, they're sampling this varying velocity field without necessarily realizing it. If most of their supernovae lie within the void, which they do because we deliberately focus on relatively nearby objects to get the most precise measurements, then the expansion rate calculation gets boosted by the outflow effect. The farther out you measure, the less our void affects the results. This predicts that the apparent expansion rate should decrease with distance, and recent observations are beginning to confirm exactly that trend. Modeling these effects requires careful calculation of how gravity works in our specific cosmic environment. Scientists must estimate the void's size, depth, and density profile, then calculate the gravitational potential field it creates throughout our region of space. That potential determines how fast material flows outward at each distance from the void center. The calculations show that a void roughly 1 billion light-years in radius with a 20% density deficit can easily produce the observed velocity patterns. The match between theoretical predictions and actual observations is compelling enough that many researchers find the void explanation more convincing than alternatives that require new physics or fundamental changes to our understanding of cosmic evolution. However, the standard cosmological model struggles to explain how such a large void could have formed in the first place. Computer simulations based on our current understanding of cosmic structure formation rarely produce voids this extreme. When they do create something similar, it requires very specific initial conditions that are statistically unlikely according to our models of how the universe evolved from the Big Bang. This raises a troubling possibility that maybe our cosmological framework is missing something important about how structure develops over cosmic time. If voids larger and deeper than expected keep showing up in observations, perhaps the process of cosmic structure formation works differently than standard theory predicts. Some scientists propose modified theories of gravity where gravitational effects are stronger on large scales, which would enhance structure formation and make extreme voids more common. Others suggest that the universe is simply more irregular and clumpy than our models assume, which would also make large voids less surprising statistically. Either way, the backwards gravity effect in voids is providing crucial information about cosmic evolution that we're still learning to interpret. Our motion through this gravitational landscape turns out to be much faster than anyone expected when the void was first discovered. The Milky Way isn't sitting calmly in space, gradually expanding with the universe. Instead, our galaxy is plummeting through the cosmos at 600,000 miles per hour, roughly 850 times the speed of sound. This tremendous velocity isn't caused by the expansion of space itself, but by local gravitational effects as our galaxy gets pulled away from under dense regions and toward areas where matter is more concentrated. The local void exerts a strong influence on our motion by creating an asymmetric gravitational environment around us. The void isn't actively pushing our galaxy away. Rather, the deficit of matter in the void means there's less gravitational pull toward it compared to the stronger gravity pulling us in other directions where matter density is higher. The denser regions win this cosmic tug-of-war, accelerating our galaxy away from the underdensity at speeds that would have seemed impossible before we understood our true cosmic environment. This velocity is difficult for most people to comprehend in practical terms. 600,000 miles per hour means the Milky Way travels about 167 miles every single second. In a year, our galaxy moves roughly 5.2 billion miles through space relative to the void structure around us. But even at this breakneck pace, the void is so incredibly vast that our motion barely makes a measurable dent in our position within it. It would take hundreds of millions of years to cross from one side of the void to the other, even moving at these extreme speeds. Meanwhile, the void itself continues expanding due to cosmic expansion and dark energy effects, growing faster than we can escape from it. We're inside this under-dense region now, and will remain inside it for the foreseeable cosmic future. This high-speed motion through space is itself powerful evidence supporting the void hypothesis. If we lived in a typical cosmic region with average matter density, our peculiar velocity would be much smaller, perhaps 100 or 200 kilometers per second at most. The fact that we're moving so extraordinarily fast indicates strong gravitational gradients in our vicinity, exactly what you'd expect from being located near a large, under-dense region. The velocity measurements are consistent with void models and would be difficult to explain through any other mechanism. This makes our galactic motion a key piece of evidence in the ongoing debate about whether our cosmic environment is genuinely unusual and whether that unusual environment affects the fundamental measurements we use to understand the universe's properties and evolution. The universe may be lying to us about its expansion rate, but it cannot hide the fact that we're racing through it at incredible speed. This motion connects to a deeper principle that our cosmic void fundamentally violates, one of the most sacred assumptions in modern physics. The cosmological principle stands as one of the foundational pillars of our understanding of the universe. This principle declares that the cosmos is homogeneous and isotropic on sufficiently large scales. Homogeneous means the same everywhere, with no location being special or different from any other when you average over large regions. Isotropic means the same in all directions. So the universe should look identical no matter which way you point your telescope. These assumptions have simplified the mathematics of cosmology enormously, allowing scientists to model the entire universe using relatively straightforward equations. Without the cosmological principle, those equations become vastly more complicated, and predictions become nearly impossible to make with any confidence. The principle has been remarkably successful throughout the history of modern astronomy, accurately describing countless observations and providing the theoretical foundation for our current understanding of cosmic evolution. But the KBC void represents a massive violation of homogeneity that threatens to shatter this fundamental assumption. If our void spans 2 billion light-years with a 20% density deficit, that constitutes an enormous inhomogeneity by any measure. Even on cosmic scales where astronomers routinely deal with structures spanning hundreds of millions of light-years, this void represents a significant fraction of the observable universe within several billion light-years of Earth. More troubling still, we happen to live near the center of this abnormal structure, which seems to contradict the core idea that our location should be unremarkable. Throughout scientific history, we've progressively removed Earth from any special cosmic position. Copernicus demonstrated that Earth wasn't the center of the solar system. Later observations revealed that our solar system wasn't the center of our galaxy, and our galaxy wasn't the center of anything significant. The cosmological principle represents the ultimate expression of this trend toward cosmic mediocrity. Not only is Earth not at any center, but there shouldn't be any meaningful center, because every location should be essentially equivalent when viewed on large enough scales. The void challenges this worldview directly. If we live inside an abnormally large, under-dense region, then our location is genuinely unusual by definition. Voids exist throughout the universe, but most are considerably smaller than our KBC void. Supervoids of this magnitude are exceedingly rare according to our current models. Finding ourselves positioned within one raises profound questions about whether the cosmological principle truly holds or whether it only applies approximately on scales much larger than we previously imagined. Some scientists calculate that in a universe governed by standard cosmological models, a void as large and deep as ours should represent what statisticians call a 10 sigma deviation from typical cosmic structure. In a random realization of universal structure, you might not encounter such an extreme void anywhere in the entire observable cosmos. Yet here we are, living inside one, and using it as our reference point for understanding how the universe works. This statistical improbability has created intense debates within the astronomical community. Defenders of the cosmological principle argue that the void doesn't actually violate the principle because homogeneity only applies at scales of several hundred megaparsecs or larger. Our void measures roughly 600 megaparsecs across, which places it right at the boundary where homogeneity is supposed to emerge. Perhaps the universe is simply less smooth at these transitional scales than our models assumed, without fundamentally violating the principle on truly cosmic scales. Alternatively, maybe the void isn't as extreme as current measurements suggest. Different observational techniques yield somewhat different estimates for the void's density contrast. If the true deficit is closer to 10 or 15% rather than 20%, the statistical rarity becomes less severe, though it remains a significant challenge for standard models. Another defense invokes what philosophers call the anthropic principle. Perhaps we shouldn't be surprised to find ourselves in an unusual location because intelligent observers can only exist in certain types of cosmic environments. This argument suggests that life requires specific conditions to develop, and those conditions might be more likely in moderately underdense regions rather than in the densest galaxy clusters or the emptiest voids. If most conscious beings throughout the universe live in mildly underdense regions, then discovering ourselves in a slight void wouldn't be particularly surprising. But this reasoning only works if our void represents a mild deviation from average density. A 20% deficit pushes well beyond what anthropic arguments can comfortably explain away. The debate over the cosmological principle remains far from settled. Some researchers believe the void is genuine and significant, requiring either substantial modifications to our cosmological models or acceptance that Earth occupies a truly unusual cosmic position. Others maintain that the void is an observational artifact, not as extreme as initially reported, or represents a temporary violation that disappears when averaged over even larger scales. Still others propose that the principle holds on scales beyond current observations, and the apparent violation will resolve itself as we map larger volumes of the universe. Future observations should help clarify this fundamental question. Deep surveys that map cosmic structure to greater distances and depths will reveal whether large voids are as rare as standard models predict, or whether they occur more frequently than expected. If extreme voids turn out to be common throughout the universe, the cosmological principle survives. But our standard model of cosmic evolution needs significant revision. If they remain genuinely rare, we face the uncomfortable task of explaining why we happen to live in such an unusual location. The origin of these vast empty regions reaches back to the universe's first moments, when quantum fluctuations smaller than atoms were stretched to cosmic proportions. During the brief period called cosmic inflation, space expanded exponentially for a tiny fraction of a second, amplifying quantum ripples from subatomic scales to dimensions spanning light years. These fluctuations created slight variations in matter and energy density throughout the early universe. Some regions ended up with density slightly higher than average, while others became slightly less dense. The variations were incredibly subtle, differing by only about 1 part in 100,000 from the cosmic mean. But gravity amplifies even the smallest advantages over cosmic time. Regions that started marginally denser attracted additional matter from their surroundings, making them denser still. This created a positive feedback loop where the rich got richer, eventually collapsing into the first stars, then galaxies, then massive clusters containing thousands of galaxies. Meanwhile, regions that began slightly less dense gradually lost matter to their denser neighbours. As material drained away toward collapsing over dense regions, the underdense areas became increasingly empty, evolving into the voids we observe today. This process, called gravitational instability, transformed barely perceptible initial variations into the dramatic, large-scale structure defining our current cosmic architecture. The cosmic microwave background radiation provides a snapshot of these density variations when the universe was merely 380,000 years old. At that ancient epoch, the variations remained tiny, visible only as slight temperature differences of about 100 microkelvin. But those temperature fluctuations correspond directly to density variations, with warmer spots indicating slightly higher density and cooler spots marking regions of lower density. Multiple space missions have mapped these temperature variations across the entire sky in exquisite detail, revealing a mottled pattern of hot and cold spots at various angular scales. This pattern encodes the seeds of all cosmic structure that would develop over the following 13.5 billion years. Scientists can take this primordial pattern and evolve it forward using computer simulations to predict how structure should appear today. Those simulations reliably produce cosmic webs of filaments, clusters, and voids that closely match current observations, representing one of the greatest successes of theoretical cosmology. However, the simulations rarely generate voids as large or as deep as our KBC void. This discrepancy creates tension between theory and observation that hasn't been fully resolved. The initial quantum fluctuations were essentially random, so every cosmic region had some probability of becoming either a void or a filament over time. But probability distributions have specific shapes that determine how often different outcomes should occur. Small voids should be common because they arise from common small-scale fluctuations. Medium voids should be less frequent, emerging from rarer medium-scale variations. Extremely large voids should be very rare, requiring exceptionally unlikely large-scale fluctuations in the initial conditions. Our void appears to fall into this extremely rare category, raising questions about whether our simulations capture all the relevant physics governing structure formation. One possibility is that the initial quantum fluctuations weren't completely random, but contained subtle correlations that enhanced the formation of large voids. This could occur if cosmic inflation didn't smooth out structure as uniformly as standard models assume, leaving behind patterns that preferentially created extreme, underdense regions. Another possibility is that gravity operates slightly differently on large scales than general relativity predicts, altering how voids form and evolve over cosmic time. A third option suggests the universe simply exhibits more variance in structure than cosmologists anticipated, making large voids statistically less surprising than current models indicate. Each explanation requires additional evidence beyond the void's existence, but the alternatives all point toward gaps in our understanding of cosmic evolution. The quantum origin of voids carries both elegance and profound implications for our cosmic situation. It means the vast empty region surrounding us traces back to subatomic processes that occurred before atoms even existed, when the universe was smaller than a proton and hotter than the core of any star. Randomness at the smallest possible scales propagated upward through gravitational amplification to create structure at the largest scales we can observe. The universe's current organization isn't designed or predetermined in any meaningful sense. It represents the consequence of random quantum fluctuations amplified by gravity over nearly 14 billion years of cosmic evolution. This realization ranks among the most profound insights of modern cosmology, but it also means our location within this structure results purely from chance. There's no fundamental reason we had to end up in a void rather than a dense filament. We exist here because the initial quantum conditions in our cosmic region happened to be slightly underdense when the universe was a fraction of a second old. That accident of quantum mechanics 14 billion years ago determines everything we observe when we look out at the cosmos today, from the distribution of nearby galaxies to the apparent rate of cosmic expansion. We're not just products of cosmic evolution, we're witnesses to it, viewing the universe through the lens of our particular quantum inheritance. The scale of these empty regions absolutely dwarfs human imagination in ways that challenge our ability to comprehend the true nature of cosmic architecture. When most people picture the universe, they imagine a sky filled with stars and galaxies stretching endlessly in all directions. But reality presents almost the exact opposite situation. The universe consists overwhelmingly of emptiness, with voids occupying roughly 90% of all available space. Galaxies and galaxy clusters crowd into the remaining 10%, packed into filaments and walls that surround the voids, like the thin edges of soap bubbles in cosmic foam. This isn't merely empty space in the sense of vacuum between individual stars within galaxies. We're talking about entire regions hundreds of millions of light years across that contain almost no galaxies whatsoever. If you could somehow travel through such a void at the speed of light, you might fly for tens of millions of years without encountering a single galaxy. The isolation would be nearly absolute, creating a cosmic loneliness that defies description. This lopsided distribution creates a profoundly unbalanced universe where most matter concentrates in a small fraction of the total volume. The dense filaments teem with galaxies that interact frequently, merge regularly, and evolve rapidly through these encounters. Star formation proceeds vigorously in these crowded environments. Supermassive black holes grow through accretion and galactic collisions. Entire galactic ecosystems develop through the constant dance of gravitational interaction. Meanwhile, the voids remain cosmically quiet. A few isolated dwarf galaxies drift through the darkness, separated by distances so vast they rarely interact with anything else. These void galaxies evolve slowly, precisely because they lack neighbors to stimulate development through gravitational encounters. They tend to be smaller, fainter, and less evolved than galaxies in dense regions, containing large amounts of unconsumed hydrogen gas that hasn't yet condensed into stars. Many void galaxies represent galactic backwaters, isolated from the busy highways of cosmic evolution that characterize the filamentary network. The extreme emptiness of voids raises fundamental questions about the nature of space itself. Even in these seemingly barren regions, dark matter maintains a presence, though at much lower concentrations than in filaments. Dark matter comprises about 85% of all matter in the universe, remaining invisible to telescopes, but detectable through gravitational effects. In voids, dark matter exists at roughly 15% of the cosmic average density. While that might sound substantial, when distributed across such enormous volumes, the actual amount of dark matter per cubic light year becomes vanishingly small. Additionally, voids contain dark energy, the mysterious component driving cosmic acceleration. Unlike matter, which clumps and clusters, dark energy appears uniformly distributed throughout space. Voids contain just as much dark energy per unit volume as dense regions, making dark energy the dominant component in these underdense areas where normal matter is scarce. The interplay between dark matter and dark energy determines void evolution over cosmic time. In the early universe, matter dominated, even in underdense regions, so gravity remained relevant for structural development. As the universe expanded and dark energy became increasingly important, voids began accelerating their expansion beyond the cosmic average. This acceleration makes voids grow faster over time, gradually consuming surrounding filaments. Eventually, if dark energy continues dominating cosmic dynamics, voids will occupy an even larger fraction of total space. The filaments will thin progressively as galaxies become more isolated islands in an expanding ocean of emptiness. Billions of years in the future, the universe will become even more hollow than it is today, with voids representing an overwhelming majority of cosmic real estate. This evolutionary trajectory appears inevitable given our current understanding of dark energy, pointing toward a future cosmos dominated entirely by emptiness. Understanding the void fraction of space proves crucial for interpreting astronomical observations correctly. When we measure average properties of the universe, such as overall matter density or expansion rate, we're averaging over both dense filaments and sparse voids. If we don't account for the fact that most space is essentially empty, we might misinterpret what those cosmic averages actually represent in terms of local conditions and universal properties. The 90% void fraction also affects searches for rare astronomical phenomena. Events like distant supernovae or gamma-ray bursts are most likely to occur in dense filaments where star formation remains active, and galaxies contain the massive stars that produce such energetic explosions. Finding these events in voids is much rarer because voids contain fewer galaxies and significantly less ongoing star formation. This creates observational selection effects that bias our cosmic surveys toward the active 10% of the universe, while largely ignoring the quiet 90%. We naturally study the universe from within its most dynamic regions, focusing on areas where interesting things happen, while overlooking the vast empty spaces that actually dominate cosmic real estate. But the voids are equally important components of cosmic reality, representing the universe's natural state of maximum entropy and minimum structure. Understanding them remains essential for developing a complete picture of how cosmic evolution operates across all environments, from the densest clusters to the emptiest reaches of intergalactic space. One particular void has emerged as especially problematic for current physics, defying probability in ways that make cosmologists profoundly uncomfortable. While our KBC void is extraordinary, it's not actually the largest underdense region known to science. That distinction belongs to the Eridanus supervoid, a cosmic desert roughly 1.8 billion light-years across. What makes the Eridanus supervoid particularly intriguing is how it was discovered. Astronomers didn't find it by counting galaxies in that region of space. Instead, they discovered it by noticing an unusually cold spot in the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. This cold spot, roughly 10 degrees across on the sky, corresponds to a region where the microwave background appears about 70 microkelvins, cooler than the surrounding average temperature. That represents a much more extreme temperature deficit than typical fluctuations from the early universe should produce. The cold spot was initially discovered by the Wilkinson Microwave Anisotropy Probe in 2005, and its existence puzzled cosmologists because its size and temperature deficit are statistically unusual. Random fluctuations from the primordial universe should occasionally create cold spots, but one this large and cold occurs in only about 2% of simulated universes. Some researchers initially proposed exotic explanations for this anomaly, including the possibility that it represented evidence of our universe colliding with another universe in a hypothetical multiverse. More conventional explanations suggested it might be a random statistical fluke or an artifact of data processing techniques. But the cold spot persisted across multiple independent observations, including data from the Planck satellite mission. A more straightforward explanation emerged when astronomers surveyed the galaxy distribution in the direction of the cold spot and found evidence for a large, underdense region, roughly aligned with it. This void, later named the Eridanus supervoid, sits approximately 3 billion light-years away from us. Light from the cosmic microwave background passes through this void on its journey to Earth, experiencing what physicists call the integrated Sachs-Wolf effect. As photons traverse the expanding void, they lose energy due to the changing gravitational environment, showing up as a temperature deficit in the observed radiation. Calculations demonstrate that a void of the Eridanus supervoid's estimated size and depth can account for roughly half of the observed cold spot temperature anomaly. The remaining temperature deficit might result from a chance alignment with a cold fluctuation in the primordial cosmic microwave background, or it might indicate that the void is larger and deeper than current measurements suggest. The Eridanus supervoid raises identical questions to our own KBC void regarding structure formation and cosmic evolution. How did such an enormous underdense region develop? Is its existence consistent with standard cosmological models, or does it require unusual initial conditions that challenge our understanding of how cosmic structure emerges? The void's reality was predicted by the cosmic microwave background cold spot before it was confirmed through direct galaxy surveys, lending credibility to its existence. But measuring its precise properties remains challenging due to its enormous distance, where galaxy surveys become incomplete and many faint objects are missed. Current estimates place the density deficit at roughly 20 to 30% compared to the cosmic average, similar to our own void. If both the KBC void and the Eridanus supervoid represent genuine extreme structures, their combined existence raises the statistical likelihood that such voids might be more common than standard cosmology predicts. Two large supervoids in the observable universe might still be consistent with current models if we allow for reasonable statistical variance in cosmic structure. But discovering 3 or 4 such extreme voids would become increasingly difficult to explain through random chance alone. The Eridanus supervoid demonstrates that voids affect observations in multiple measurable ways. The temperature deficit they create in the cosmic microwave background, radiation is subtle but detectable with sufficiently sensitive instruments. The velocity fields they generate produce observable effects in galaxy motions and bulk flow measurements. These phenomena aren't merely theoretical predictions existing only in computer simulations. They represent real physical processes that astronomers can study and quantify through careful observation. This provides hope that the mysteries surrounding void physics and their impact on cosmological measurements can eventually be resolved through better data and more sophisticated analysis techniques. If voids systematically affect our measurements in predictable ways, those effects can potentially be corrected for or properly modelled in cosmological calculations. The challenge lies in obtaining sufficient observational data to characterize the void structure of the universe with the accuracy needed for such corrections. One conclusion seems increasingly clear as more voids are discovered and characterized. The universe contains significantly more large-scale empty structure than early cosmological models anticipated. Whether this reflects the genuine rarity of our cosmic neighborhood or reveals inadequacies in our theoretical understanding of structure formation remains an open and actively debated question. Our measurements become deeply suspect when we realize they're only reliable beyond the boundaries of our cosmic bubble. Scientists have identified what they're calling the Hubble bubble, a troubling observational pattern that reveals the systematic bias affecting our understanding of cosmic expansion. When astronomers measure the expansion rate using nearby objects within roughly 2 billion light-years of Earth, they consistently obtain higher values, around 73 kilometers per second per megaparsec. But when they use objects farther than 2 billion light-years, or rely on cosmic microwave background data from the early universe, they get lower values around 67 kilometers per second per megaparsec. The boundary, at approximately 2 billion light-years, is suspiciously close to the estimated edge of our void. This has led researchers to propose that measurements within the void suffer from systematic bias due to our unusual environment, creating a bubble of distorted observations that doesn't represent universal truth. Only by looking beyond this bubble can we glimpse what the universe's expansion actually looks like from a more typical cosmic location. This hypothesis makes a testable prediction that's both elegant and disturbing. The measured expansion rate should vary systematically with distance from our position. Nearby measurements should show the highest values as they're most affected by our void environment. As observations extend farther out, approaching and eventually crossing the void's edge, the measured expansion rate should gradually decline toward the true cosmic average. Beyond 2 billion light-years, it should stabilize at the lower value that represents universal rather than local properties. Recent observations are beginning to confirm exactly this predicted trend. Studies using exploding stars at various distances find that the inferred expansion rate decreases with increasing distance, though the effect remains at the edge of current measurement precision. The trend isn't yet definitive, because measuring distances to very remote supernovae pushes our technology to its limits, creating large uncertainties that make the pattern difficult to establish conclusively. But the direction of the observed trend matches void model predictions perfectly. If the Hubble bubble represents reality, it creates a profound problem for cosmological research. Most measurements of local cosmic properties necessarily focus on nearby objects, because those are the only ones we can observe with sufficient detail and precision. Distant objects appear fainter and become increasingly difficult to characterize accurately, forcing astronomers to rely heavily on local measurements for their most reliable data. But these local measurements are precisely the ones most contaminated by our void environment. We're trapped inside the bubble, unable to step outside our local cosmic environment to observe what the universe truly looks like from a more representative location. The situation resembles trying to determine Earth's global climate by only measuring temperatures inside a heated building. You can make extremely precise local measurements, but they fundamentally misrepresent the planetary average. Breaking out of the Hubble bubble requires observing objects well beyond 2 billion light-years, with precision comparable to nearby measurements. This represents an enormous technological challenge that's only recently become feasible. Space telescopes like James Webb can observe distant supernovae with unprecedented detail, while ground-based observatories with massive mirrors and advanced instruments are discovering bright objects at extreme distances. These distant probes offer windows into the universe beyond our local bubble, and early results suggest the far universe expands at rates predicted by cosmic microwave background models rather than local measurements. This supports the bubble hypothesis, though much more data is needed to establish the trend definitively. The bubble concept extends beyond expansion measurements to other cosmological observations. Bulk flow studies show significant galaxy motions out to roughly 300 million light-years, but these flows appear to decline at larger distances, consistent with void-generated velocity fields that dissipate near the void's boundary. Baryon acoustic oscillation measurements, which use sound waves from the early universe as cosmic rulers, show discrepancies primarily at low distances, again suggesting local environmental effects rather than universal phenomena. Multiple independent lines of evidence point toward the same unsettling conclusion. Our local cosmic environment, within approximately 2 billion light-years, differs systematically from the universe at large. We inhabit an island of unusual properties surrounded by a more typical cosmos that we can barely observe directly. Accepting the Hubble bubble hypothesis requires acknowledging that many measurements we use to understand universal properties are biased by our cosmic address. This philosophical discomfort reflects scientists' preference for believing their observations represent universal truths, rather than local accidents of cosmic geography. But mounting evidence suggests We cannot escape this local bias without extending observations far enough that our void's influence becomes negligible. Future surveys probing beyond 2 billion light-years will prove crucial for confirming whether the bubble is genuine and whether it fully explains the expansion rate crisis. If it does, cosmology can breathe easier, knowing the standard model works correctly, and we simply happen to be measuring from an unusual location. If the tension persists even at vast distances, entirely new physics will be required to explain the fundamental disagreement. The void creates more than measurement bias. It actively filters the types of cosmic structures that can form within its boundaries. Dense regions of the cosmic web experience frequent galaxy collisions and mergers that drive rapid evolution, transforming small irregular galaxies into massive elliptical systems over billions of years. Galaxy clusters form as smaller groups merge under mutual gravity, creating rich concentrations containing thousands of galaxies surrounded by hot gas that glows in X-rays. Supermassive black holes grow through accretion of material stirred up by galactic encounters, eventually becoming the powerful engines that drive active galactic nuclei. This represents the normal trajectory of structure formation in environments where matter density exceeds cosmic averages. But in voids, this evolutionary pathway becomes blocked by insufficient gravity. The low matter density means gravitational forces remain too weak to assemble massive structures. Small structures, like individual galaxies, can still form because the initial density fluctuations that seeded them were strong enough to overcome cosmic expansion in their immediate vicinity. But larger structures requiring more gravitational attraction than sparse void environments can provide simply cannot develop. Rich galaxy clusters containing thousands of members cannot form in regions where matter density is 20% below average. The mathematics of gravitational collapse prevents such massive concentrations from assembling in under-dense environments, creating an effective ceiling on structural development. Voids remain perpetually stuck in evolutionary states that dense regions passed through billions of years ago. The largest structures that manage to form within them are modest galaxy groups containing perhaps a few dozen members at most, while the massive clusters that characterize rich cosmic environments remain impossible. This filtering effect profoundly influences galaxy evolution within void environments. In dense regions, frequent mergers consume galactic gas supplies and shut down star formation, transforming blue star-forming spirals into red elliptical galaxies filled with old stellar populations. But in voids, mergers occur rarely if ever. Galaxies retain their gas supplies and continue forming stars slowly over cosmic time, remaining blue and actively star-forming much longer than their counterparts in clusters. This explains why void galaxies tend to be late-type spirals with ongoing star formation rather than early-type ellipticals dominated by ancient stars. The filter also affects the intergalactic medium, the diffuse gas pervading space between galaxies. In dense regions, this material gets heated to millions of degrees by shocks from galaxy collisions and energy output from supermassive black holes, creating the hot ionized plasma that emits X-ray radiation. In voids, the intergalactic medium remains cooler and denser, preserving conditions closer to those in the early universe. This makes voids excellent natural laboratories for studying primordial gas and understanding how it gradually incorporates into galaxies through cosmic time. The cooler gas in void environments is more likely to remain in neutral atomic form, particularly hydrogen, which can be detected through characteristic radio wavelength emissions. Surveys of neutral hydrogen in voids have revealed filamentary structures connecting the few galaxies present, representing remnants of cosmic web architecture on smaller scales. The filtering effect becomes self-reinforcing because massive structures cannot develop in void environments. The underdense regions remain essentially unchanged over cosmic time, lacking the rich clusters needed to pump energy into surrounding space or drive the complex feedback processes that characterize dense environments. There are no massive galaxies to generate powerful stellar winds that expel gas across large distances. No active galactic nuclei to heat intergalactic gas to X-ray emitting temperatures. The void maintains its quiet, underdeveloped character indefinitely, while dense regions continue evolving toward ever greater complexity and richness. This creates increasing contrast between voids and filaments over cosmic time, with empty regions becoming progressively more isolated, while dense areas grow richer and more structured. Dark energy acceleration amplifies this trend by speeding void expansion, causing them to consume surrounding territory while concentrating matter into increasingly narrow filamentary networks. The concept of cosmic filtering has implications that extend beyond structure formation to fundamental questions about life in the universe. If advanced civilizations require specific environmental conditions, such as stable galaxies with sustained star formation, void regions might actually prove more hospitable than dense environments. Void galaxies experience fewer catastrophic events, like nearby supernovae or gamma-ray bursts that could sterilize planets within thousands of light-years. The isolation provides long-term stability that dense cluster environments cannot offer, where galactic encounters and violent phenomena occur much more frequently. On the other hand, the reduced rate of star formation in void galaxies means fewer opportunities for heavy element production and planet formation. Void galaxies tend to be metal-poor compared to their counterparts in rich environments, potentially limiting the types of rocky worlds that can develop. Whether voids enhance or diminish prospects for biological evolution remains an open question that connects cosmic structure to astrobiology in ways scientists are only beginning to explore. But if we do live in a void, it might influence both our galaxy's properties and the specific conditions that allowed Earth's development. The future evolution of void regions points toward increasing cosmic isolation as dark energy continues accelerating universal expansion. Space expands faster over time, and this acceleration carries dire implications for the far future of cosmic structure and connectivity. Structures not gravitationally bound together will drift apart and eventually lose all contact as the space between them stretches beyond any possibility of communication or interaction. This process operates currently but will intensify dramatically over coming billions and trillions of years. Voids expand faster than the universe as a whole, precisely because they contain insufficient matter to resist the acceleration. Surrounding filaments will thin progressively as galaxies within them separate by ever-increasing distances, eventually losing the gravitational connections that currently define cosmic web architecture. Even neighboring superclusters will lose causal contact as space between them expands faster than light can travel the growing distances. The universe's ultimate fate appears to be increasing isolation, with all structures becoming islands separated by exponentially expanding voids. For galaxies within existing voids, this isolation will become profound beyond current imagination. Today, galaxies in our void can still observe surrounding filaments and clusters in the distance, with light from those structures reaching us after traveling for billions of years across intervening space. But as dark energy drives accelerating expansion, light from increasingly distant objects will never reach us before the universe expands too much for the radiation to bridge the growing gaps. The cosmic horizon, representing the boundary beyond which light cannot reach us, will shrink progressively over time. Objects currently visible will fade from view as their light gets stretched to undetectable wavelengths. Galaxies deep within voids will find themselves in increasingly empty skies with fewer and fewer neighbors remaining observable through any means. The cosmic microwave background radiation will grow cooler and dimmer as its photons stretch to longer wavelengths, eventually becoming too faint to detect with any conceivable technology. This raises disturbing questions about the cosmic knowledge available to future civilizations. If intelligent beings arise in void galaxies billions of years from now, what will they be able to learn about universal properties? Their sky will appear nearly empty, except for their immediate galactic neighborhood. The cosmic microwave background will be undetectable, eliminating evidence for the Big Bang. There will be no distant galaxies to measure cosmic expansion, no supernova to trace acceleration history, no large-scale structure to reveal the cosmic web's architecture. Such civilizations might conclude they inhabit a static island universe, surrounded by empty space, never suspecting the vaster cosmos beyond their observable horizon. This scenario, sometimes called the Cosmic Dark Age, represents the inevitable consequence of accelerating expansion driven by dark energy. Even within our current void, the long-term outlook appears increasingly lonely as cosmic evolution progresses toward ultimate isolation. The Milky Way and Andromeda will merge in roughly 4 billion years, forming a giant elliptical galaxy that will dominate our local group. But this merged system will become progressively isolated as other nearby structures recede beyond observable limits within tens of billions of years. Star formation will gradually cease as gas supplies are consumed or expelled, leaving only aging stellar populations that slowly fade over cosmic time. The night sky will darken as fewer active stars remain to illuminate the cosmic void surrounding our island of matter. On even longer timescales measured in trillions of years, stars will become increasingly rare as nuclear fuel supplies are exhausted. Galaxies will consist mainly of stellar remnants slowly dispersing through gravitational interactions, while black holes grow by accreting whatever material remains accessible. Eventually, even black holes will evaporate through quantum processes, leaving behind a diffuse sea of particles and radiation expanding forever into darkness. Voids will have consumed everything, with the last remnants of cosmic structure dissipating into infinite, empty expansion. This bleak future lies billions of years away and depends on dark energy maintaining its current, accelerating influence. If dark energy changes strength or reverses sign, different outcomes become possible. But present observations suggest dark energy behaves as a cosmological constant, providing unrelenting acceleration that will ultimately reduce the universe to void-dominated emptiness. The cosmic web we observe today, with its intricate filaments and rich clusters, represents a temporary phase in universal evolution. The true long-term structure appears destined to be emptiness, punctuated by isolated islands of matter growing ever more remote from each other across exponentially expanding space. We live during an unusual epoch when the universe still maintains rich structure, and voids represent interesting features rather than dominant reality. Billions of years hence, voids will constitute essentially everything, making our current cosmic neighborhood a fleeting arrangement that future civilizations may never have the opportunity to observe or understand. If other civilizations exist within cosmic voids throughout the universe, they face the same fundamental challenge we're confronting right now. The question of whether void-dwelling civilizations can develop accurate cosmological understanding becomes deeply troubling when you consider the systematic biases affecting every measurement they could possibly make. A civilization emerging in a dense galaxy cluster would observe rich structure stretching in every direction. Their night sky would be crowded with neighboring galaxies, making cosmic expansion relatively straightforward to discover and measure. For them, developing the Big Bang model would feel natural and inevitable because the evidence would be overwhelming and consistent. But a civilization deep within a void might struggle with exactly the problems we're facing. With few nearby galaxies to observe, measuring cosmic expansion becomes extraordinarily challenging. The void's effect on local measurements could lead them to completely incorrect conclusions about universal properties. They might develop alternative cosmological models that attempt to explain their observations without invoking cosmic expansion or dark energy. Imagine trying to understand the ocean while trapped inside a small boat with no view of the horizon. You might conclude that water naturally moves in circles because that's all you can observe from your limited perspective. This raises the unsettling meta question of whether our own cosmological understanding suffers from biases we haven't yet recognized. We think we comprehend the universe fairly well based on observations made from within the KBC void. But what if systematic errors permeate our measurements in ways we can't detect? What if the universe beyond our void looks fundamentally different from what we observe locally? Our entire framework for understanding cosmic evolution, dark energy, and the ultimate fate of the universe might be built on measurements that don't represent universal truth. Future observations extending well beyond our void's boundaries will provide the crucial test of whether void dwellers can accurately understand the cosmos. If distant regions confirm our local conclusions, we can feel confident our understanding reflects universal reality. If they reveal systematic differences, we may need to completely overhaul our cosmological framework. The search for life throughout the universe has traditionally focused on habitable zones around stars, atmospheric signatures on distant planets, and radio signals from technological civilizations. Perhaps it should also consider the large-scale cosmic environment where life might emerge and evolve. If voids provide more stable conditions for biological development, then civilizations within these regions might be more common than we expect. The reduced frequency of catastrophic events, like nearby supernova or gamma-ray bursts, could make void galaxies excellent nurseries for complex life that requires billions of years of stable conditions to evolve. Alternatively, if voids lack sufficient resources for technological development due to their lower metallicity and reduced star formation rates, advanced civilizations might be concentrated primarily in dense regions where raw materials are abundant and energy sources are readily available. The distribution of intelligence throughout the universe could follow patterns we've never considered, with most advanced civilizations clustering in specific types of cosmic environments, while others remain largely barren despite containing billions of potentially habitable worlds. If we represent typical void dwellers, other intelligent species might also be questioning whether their cosmological measurements are distorted by location. They might be searching for signals from beyond their local voids, hoping to contact civilizations with different perspectives on universal properties. The cosmic web structure influences not just where we should look for life, but how that life might understand its place in the universe. Each type of cosmic environment creates its own observational challenges and opportunities that shape the development of scientific understanding. We might be part of a vast community of void civilizations, all struggling with similar measurement biases and all wondering whether they're seeing the universe accurately. The silence we experience in our searches for extraterrestrial intelligence might reflect not the absence of other civilizations, but the difficulty of communication across the enormous distances that characterize void environments. The loneliness we feel when contemplating our cosmic situation might be shared by countless other species scattered throughout the universe's empty regions, each one questioning their cosmic significance while surrounded by the same troubling emptiness that defines our local neighborhood. Recent advances in understanding baryon acoustic oscillations have provided some of the most compelling evidence for our void's influence on cosmological measurements. These represent frozen sound waves from the infant universe that serve as cosmic rulers for measuring distances across billions of light years. In the first 380,000 years after the Big Bang, the universe existed as hot plasma where matter and radiation remained coupled together. Sound waves rippled through this primordial medium, creating oscillations in density that propagated at roughly half the speed of light. When the universe cooled enough for atoms to form, these sound waves froze in place, leaving permanent imprints on the distribution of matter. The characteristic distance these waves travelled before freezing appears as a standard scale in galaxy clustering patterns, roughly 490 million light-years across. This scale shows up consistently in galaxy surveys, regardless of distance or cosmic epoch, providing astronomers with a reliable measuring stick for cosmic geometry. Unlike other distance measurement techniques that rely on object brightness and can be affected by dust or systematic errors, Baryon acoustic oscillations offer purely geometric measurements. By comparing the apparent size of this characteristic scale at different distances, scientists can map how the universe has expanded throughout cosmic history. It's equivalent to placing identical rulers at various distances and measuring how large they appear, revealing whether expansion is accelerating, decelerating, or remaining constant. Using this technique, researchers have created three-dimensional maps of galaxy distribution spanning billions of light-years. These maps reveal the cosmic web in unprecedented detail while also confirming the existence of our local void through independent measurements. When scientists analyze galaxy clustering in our cosmic neighborhood and compare it to Baryon acoustic oscillation predictions, they find clear evidence for the density deficit that defines void regions. The void appears as a region where observed clustering differs systematically from distant measurements. The Baryon acoustic oscillation scale looks different when measured within our void compared to measurements made at greater distances, where our local environment's influence becomes negligible. This mismatch provides independent confirmation that we reside in an underdense region that affects local observations. The precision of these measurements continues improving with new surveys like the Dark Energy Spectroscopic Instrument, which began operations recently and is mapping tens of millions of galaxies with unprecedented accuracy. These observations will determine void properties to within a few % uncertainty over the next several years. That level of precision will either definitively confirm the void as the explanation for cosmological tensions or reveal additional complications requiring further theoretical development. Either outcome will advance our understanding of cosmic structure and its influence on fundamental measurements. The Baryon acoustic oscillation technique has also revealed something unexpected about cosmic expansion history. Measurements at different epochs show slight deviations from predictions based on early universe observations, with the largest discrepancies appearing at recent cosmic times. These deviations align precisely with expectations for observations made from within a large void, where local expansion rates should exceed the cosmic average due to gravitational effects. The pattern strengthens the case that our unusual location systematically biases multiple independent measurement techniques. The temperature of space itself carries signatures of our void that extend far beyond simple galaxy counting. The cosmic microwave background radiation permeates the entire universe, with faint light left over from the Big Bang, maintaining a nearly uniform temperature of just 2.7 degrees above absolute zero. But this uniformity isn't perfect. Tiny temperature variations exist across the sky, typically differing by only millionths of a degree from one direction to another. These fluctuations encode crucial information about cosmic structure and evolution that satellites have mapped with exquisite precision. Hotspots in this radiation correspond to regions that were slightly denser in the early universe, while cold spots mark areas that were less dense. Over billions of years, these initial variations grew into the cosmic web of filaments and voids we observe today. The cosmic microwave background also reveals evidence for voids through subtle temperature effects. Light from this ancient radiation travels through whatever cosmic structure has formed along its path to reach our telescopes, experiencing different gravitational influences depending on the environment it traverses. When photons pass through voids, they experience what physicists call the integrated Sachs-Wolf effect. The reduced gravity in underdense regions creates measurable changes in photon energy that show up as temperature variations in the observed radiation. As light enters a void, it gains a tiny amount of energy from the gravitational potential. As it exits, it loses energy. Normally these effects would cancel perfectly, but void expansion during the photon's transit creates an imbalance that leaves the light slightly cooler than it started. This effect is incredibly subtle, but becomes detectable when averaged over many voids. Astronomers have identified large voids throughout the nearby universe using galaxy surveys, then examined cosmic microwave background temperature in those directions. The correlation is statistically significant and matches theoretical predictions perfectly. Void regions consistently show temperature deficits of about 10 microkelvin compared to cosmic averages, confirming that these empty regions do affect fundamental radiation properties. For our specific void, the effect should be particularly strong because light from the cosmic microwave background passes through nearly our entire local, under-dense region on its journey to Earth. This accumulates temperature changes over the full billion light-year extent of our cosmic neighborhood. The temperature measurements also constrain our void's properties by providing upper limits on how extreme it can be. If the void were much larger or deeper than current estimates suggest, it would create stronger temperature signals that should already be clearly visible. The fact that no dramatic temperature anomaly appears in our direction places boundaries on void characteristics that remain consistent with other measurement techniques. This agreement between independent approaches strengthens confidence in our understanding of local cosmic structure. One of the most intriguing features discovered in cosmic microwave background maps is an unusually large cold spot that some researchers have connected to supervoid effects. This region appears roughly 5 degrees across on the sky and shows temperature deficits exceeding typical early universe fluctuations. Some scientists propose this cold spot results from an extremely large void along that particular line of sight, though the connection remains controversial because such a supervoid would itself be statistically improbable, according to standard cosmological models. Our void doesn't align with this famous cold spot because it surrounds us in all directions rather than appearing in one specific region. Its temperature signature therefore shows up as modifications to overall cosmic microwave background patterns rather than localized anomalies. The gravitational effects we experience within our void have led some scientists to question whether our understanding of gravity itself requires revision. Einstein's general relativity has passed every experimental test for over a century, forming the foundation for all modern cosmological models. But if voids as large and deep as ours cannot arise naturally under standard gravity and matter models, perhaps gravitational physics works differently on the largest cosmic scales than Einstein predicted. Some researchers propose modifying gravity rather than accepting we live in a statistically improbable location. Modified theories of gravity, such as modified Newtonian dynamics or MOND, suggest that gravitational behavior changes when accelerations become extremely small. At the tiny accelerations relevant for galaxy outskirts and cosmological structure, gravity might be stronger than general relativity predicts. This modification was originally proposed to explain galaxy rotation curves without requiring dark matter, though it has struggled to account for many other cosmological observations. However, MOND performs better than expected at predicting certain features of large-scale structure formation. In MOND cosmology, structures form more efficiently because enhanced gravity on large scales pulls matter together more effectively. This naturally produces richer superclusters and deeper voids compared to standard gravity models, potentially making extreme voids like ours less statistically surprising. Computer simulations using modified gravity create voids as large as our KBC void without requiring unusual initial conditions, resolving the tension between observations and theory by changing the underlying physics rather than invoking extreme luck. This represents an attractive feature because it eliminates statistical improbability while preserving most successful aspects of current cosmological models. However, modified gravity theories face serious challenges in explaining other observations like cosmic microwave background fluctuations. The debate between modified gravity and standard cosmology with statistical outliers remains unresolved. Proponents argue that repeatedly finding structures too large according to standard models indicates those models require fundamental revision. Defenders of conventional physics argue that modified gravity creates new problems while solving old ones, preferring to accept unusual locations rather than overthrowing established gravitational theory that works excellently in other contexts. Future observations should help resolve this debate by determining whether large voids and extreme structures are genuinely more common than current models predict, or whether they remain rare enough to preserve standard physics while forcing us to accept cosmological mediocrity. The void's existence has created a crisis regarding the age of the universe that extends far beyond academic curiosity. Current measurements based on cosmic microwave background observations place the universe's age at 13.8 billion years, derived from detailed models of cosmic expansion history. These models use expansion rates measured from early universe conditions, along with matter and dark energy densities, to calculate how long ago the Big Bang occurred. The result has been verified through multiple independent analyses and represents one of cosmology's most reliable numbers. But if local expansion measurements are genuinely faster than cosmic averages due to void effects, those age calculations could be systematically wrong. If the higher local expansion rate of 73 kilometers per second per megaparsec represents universal truth rather than environmental bias, cosmic expansion has been faster throughout history. Faster expansion means the universe reached its current size in less time, making it roughly 8% younger at approximately 12.7 billion years old instead of 13.8 billion. This difference creates immediate conflicts with stellar evolution observations. The oldest stars in globular clusters appear to be about 13 billion years old based on well-tested stellar physics models. You cannot have stars older than the universe itself, creating an impossible situation that demands resolution through revising either stellar ages or cosmic ages. Stellar age measurements depend on understanding how stars evolve over billions of years, burning nuclear fuel at rates determined by their mass and composition. Low-mass stars last hundreds of billions of years, while high-mass stars exhaust themselves in mere millions of years. By observing which stellar masses have reached the end of their lives in ancient globular clusters, astronomers can estimate when all stars in those clusters originally formed. The oldest clusters show that their most massive surviving members are barely still burning hydrogen, indicating cluster formation roughly 13 billion years ago. These measurements rely on stellar physics that has been extensively tested and verified through observations of stars at various evolutionary stages. Small uncertainties exist in how efficiently stars mix their interior material or lose mass through stellar winds, but major systematic errors seem unlikely. The age tension, like the expansion rate tension, might be resolved if local measurements don't represent global averages. If void effects inflate our local expansion rate measurements, the cosmic microwave background age estimate of 13.8 billion years could remain correct for universal properties. This resolution requires accepting our unusual cosmic location, which troubles scientists philosophically but avoids requiring major changes to stellar physics or early universe cosmology. It preserves the successful aspects of current models while attributing discrepancies to environmental effects. Alternatively, both measurements could contain partial truth if dark energy has evolved over cosmic time. If dark energy was weaker in the past and became stronger recently, early expansion would have been slower, while recent expansion appears accelerated due to both dark energy evolution and void effects. The age issue highlights broader interconnections throughout cosmological parameters. Changing the expansion rate affects not just universe age, but also matter density, dark energy properties, and structure formation predictions. You cannot adjust one parameter without affecting others in ways that might create new problems. The void offers a way to preserve most standard model predictions by attributing discrepancies to location rather than fundamental physics, but it doesn't completely eliminate age tensions because some evidence for cosmic age comes from objects within our void that should be unaffected by expansion measurement biases. Ancient starlight from the oldest stars in our galaxy creates another challenge for any cosmological model that makes the universe significantly younger. These primordial stars, found mainly in globular clusters and the galactic halo, contain very few elements heavier than hydrogen and helium. The first stars formed from pure primordial material left over from Big Bang nuclear synthesis. Through nuclear fusion, they created heavier elements and scattered them throughout space when they died as supernova. Subsequent stellar generations incorporated these metals, gradually increasing galactic chemical enrichment over cosmic time. The most metal-poor stars observable today must have formed very early, before significant chemical evolution occurred. Their ages provide direct measurements of how long ago our galaxy began forming stars, offering independent constraints on cosmic chronology. These stellar ages consistently indicate formation times around 12.5 to 13 billion years ago, using multiple independent techniques that don't rely on cosmic expansion measurements. The agreement between stellar ages and cosmic microwave background universe ages suggests both reflect genuine cosmic chronology. If void effects explain expansion rate discrepancies without affecting stellar age measurements, the consistency between different age determination methods supports cosmic microwave background estimates over local expansion rate calculations. This internal coherence strengthens the void hypothesis as a resolution to cosmological tensions. The motion of galaxies across vast cosmic distances reveals another layer of evidence supporting our unusual environment. Peculiar velocities represent galaxy motions beyond simple cosmic expansion, driven by gravitational attraction toward dense structures and repulsion from under-dense regions. In standard cosmological models, these peculiar motions should remain relatively small and random when averaged over large scales. Nearby galaxies might move at a few hundred kilometers per second due to local gravitational effects, but bulk flows should approach zero when measured across hundreds of millions of light years. This expectation follows from the cosmological principle's assumption that the universe is homogeneous on large scales. If matter distribution is truly uniform beyond a certain scale, there should be no coherent large-scale gravitational gradients to drive systematic bulk motions. Observations tell a dramatically different story. Measurements of galaxy velocities using multiple independent techniques reveal significant bulk flows extending to distances of 2 to 300 million light-years, reaching velocities of 400 kilometers per second or more. These flows are not only large but coherent, meaning galaxies across enormous volumes move in roughly the same direction. This indicates the presence of large-scale gravitational gradients that pull matter towards specific regions while pushing it away from others. Our void provides exactly the kind of asymmetric mass distribution that could generate such flows. Material within under-dense regions accelerates outward towards surrounding dense structures, creating bulk motion patterns that extend throughout the void volume. The observed bulk flows match predictions from models that include our void's gravitational effects. When researchers simulate galaxy motions within a large under-dense region surrounded by normal density structures, predicted velocities and flow directions closely match actual measurements. Standard cosmology without void effects struggles to explain flows of this magnitude and coherence. Simulations based on typical cosmic structure predict bulk flows should decline rapidly with increasing scale, reaching less than 100 kilometers per second when averaged over 200 million light-year volumes. The discrepancy between predicted and observed bulk flows represents another challenge to standard models that the void hypothesis naturally resolves. Enhanced structure formation through modified gravity could also explain larger flows, though this requires changing fundamental physics rather than accepting unusual locations. Future surveys measuring bulk flows at even greater distances will provide crucial tests of these competing explanations. If flows remain strong beyond 300 million light-years, it would further challenge standard cosmological assumptions about large-scale homogeneity. The bulk flow observations demonstrate that our cosmic environment is more dynamic and structured than simple uniform models assume. Whether this reflects our unusual void location or indicates systematic problems with cosmological models depends on how these measurements develop as observational capabilities improve. We find ourselves at an extraordinary moment in cosmic history, living during the brief epoch when the universe still maintains rich structure, visible across vast distances. The void around us may be vast and largely empty, but we can still observe the filaments and clusters that define the cosmic web, stretching billions of light years in every direction. This won't always be true. The accelerating expansion driven by dark energy will eventually stretch space so much that light from distant structures will never reach future observers. The cosmic horizon will shrink over time as more and more of the universe disappears beyond our ability to detect it. Civilizations that emerge in our cosmic neighborhood billions of years from now will inherit a much darker and more isolated universe. They'll see only their immediate galactic surroundings, with no evidence of the vast cosmic architecture that we can still barely glimpse today. The cosmic microwave background radiation will fade to undetectable levels. The baryon acoustic oscillation, signals that currently provide our most reliable distance measurements, will disappear. Even the largest structures in our current cosmic web will recede beyond any possible observation. Future scientists will find themselves in what amounts to a perfect void, surrounded by apparent emptiness with no way to discover the broader cosmic context that we're still struggling to understand. They might conclude they live in a static, island universe with no expansion, no Big Bang, and no cosmic evolution. We're living during a unique window when the universe's full complexity remains partially accessible to observation and scientific investigation. The measurements we make today about cosmic expansion, structure formation, and fundamental physics represent knowledge that may become impossible to acquire in the far future. This places an almost overwhelming responsibility on our current generation of cosmologists and astronomers. We're not just trying to understand the universe for our own curiosity and advancement. We're potentially the last observers who will ever have access to the complete cosmic story. Every telescope we build, every survey we conduct, every measurement we make adds to a cosmic library of knowledge that future civilizations may never be able to recreate. The data we collect about distant galaxies, cosmic expansion, and large-scale structure represents a precious record of universal properties that will eventually become unobservable. The void around us makes this responsibility even more poignant. If our measurements are systematically biased by our unusual location, we face the challenge of extracting universal truth from local observations before that opportunity disappears forever. The universe is teaching us about its deepest secrets through the very environment that may be misleading us about its true nature. We must learn to see beyond our cosmic address to glimpse the broader reality that will remain hidden from all future observers in our corner of space. So here we are, falling through a cosmic hole 2 billion light-years wide, and most of humanity still has no idea. We've journeyed through one of the most unsettling discoveries in modern astronomy, a revelation that challenges everything we thought we knew about our place in the universe. The KBC void isn't just empty space, it's a fundamental challenge to our understanding of cosmic reality. Every measurement we've ever made about the universe's expansion rate might be distorted by our unusual location. Every conclusion we've drawn about dark energy, cosmic age, and the ultimate fate of the universe might reflect local environmental effects rather than universal truth. We're not passive observers of cosmic evolution. We're participants in it, carried along by forces so vast they dwarf our ability to step outside and see the universe objectively. The Milky Way races through this emptiness at 600,000 miles per hour, driven by gravitational imbalances that reveal just how extraordinary our cosmic neighborhood really is. Whether this void explains the greatest crisis in cosmology or forces us to completely revise our understanding of fundamental physics, one thing remains certain. The universe is far stranger than we ever imagined, and our place within it is more unusual than we dared suspect. The next time you look up at the night sky, remember that those points of light are scattered islands in a cosmic desert of nearly incomprehensible scale. We're cosmic castaways drifting through an ocean of emptiness, measuring a reality that might be fundamentally different from